Hello, AP Calculus students. We are about to start the final unit of this course, Unit 10, about applications of integration. As far as the importance of this unit goes, this is a particularly important unit for the free response part of the AP exam. As I've told you a couple times, there are 6 free response questions. Most years, at least 3 of them come from information in this unit, so this is a big deal. Why is this unit so important? Well, because this unit will use ideas that were introduced in other units along the way. So we're starting Unit 10, Applications of Integration, although we'll also throw a couple derivatives in there. And this first topic that we're going to spend 2 days on, we're just going to call Calculus in Context. Basically like real-world applications of derivatives and integrals. And I think we're gonna jump right into this. This does not match up with a section in your book. The book does not really cover these things, even though this is a huge focus on the exam. So I'm just gonna sort of do my own thing here. First of all, given a function, f of x, we have 2 different types of rates of change that we've talked about in this class. We've talked about the average rate of change, and we've talked about the instantaneous rate of change. Given a function, its average rate of change on the interval from a to b is given by, and we've seen this formula several times this year, f of b minus f of a over b minus a, our average rate of change, our average slope. Given a function f of x, its average rate of change on the interval from a to b is f of b minus f of a over b minus a, as opposed to its instantaneous rate of change, rate of change at x equals a. What's the rate of change right at one specific instant? Well, that's just the derivative. The instantaneous rate of change at x equals a is f prime of a. And this can also tell us how our original function is increasing or decreasing. Tells us how that original function I gave you, f of x, is increasing or decreasing. Average rate of change of a function, f of b minus f of a over b minus a. Instantaneous rate of change right at one specific instant, is just given by the derivative. Finally, both of these have units of. The units are going to be the units of f of x divided by the units of x. Everything we look at here will have units to it. The units are the units of f of x, although units of f of x, and you can just leave that in the green thing on the side, divided by the units of b minus, hold on, let me think for a moment. The units of f of x divided by the units of x. That formula is the same formula we use to kind of create our derivative stuff. You guys can come in. Sorry, I've got student council people in and about. They say hello. They'll watch the video tomorrow. Okay. What was I doing? I think I'm going to make the video pause through Edpuzzle so you can make sure this is all in your notes, and we'll go from there. Thank you. You too. So the next thing that I need you to do is I need you to get out the packet in the Unit 10 stuff titled Calculus in Context, in-class examples. I'll make the video pause again so you can get that out. Okay, and let's take a look here. In problem number 1, water is flowing into a tank so that the volume of water in the tank at any time is given by this function. You plug in a time, we get our volume. In part A, I want to know at what rate is the amount of water in the tank changing after 15 seconds. Well, the rate of change, or here the instantaneous rate of change right at 15 seconds, is the derivative. What we need to do is find the derivative at time 15, v prime of 15. Now, I've avoided talking about this all year, but it's finally time for me to show you how we can use the graphing calculators to do derivatives, and then a little bit later today I'm going to show you how to do integrals. Please get out your graphing calculator. Again, I'll make the video pause so you can go do that. Okay, I want to find the derivative of that function that was given when v equals 15. I'm not sure if this is how clear this is going to show up, but I'm going to see what I can do. If you go on the graphing calculator and push the math button, wow, that's really not going to show up great. Let me use the other calculator, sorry about that. If you go on the calculator, push the math button, go down in the math pull down to option number 10 that says n deriv, and push enter. Your calculator might say n deriv, or it might give you some symbols that look like this, kind of look like derivative symbols. If your calculator says n deriv, this is going to take 3 arguments. We first need to tell it the function I want to find the derivative of, then I need to tell it the variable, then I need to tell it where do I want to find the derivative. You know what? Hold on 1 second. I just need to check about something for 1 moment. Keep working. I don't know anymore. Okay, it takes 3 arguments. I'm first going to type in the function 74 minus 9, e raised to the negative 0.3 x. I'm using x rather than t, whatever. Then, comma x, then comma the value where you want to find the derivative. And if we push enter, it's going to give us our derivative, about 0.02999. Let me write that down. If you have one of the newer calculators, you're going to get something that looks like this. You're still going to fill in all the information, just in a slightly different way. dd, well, I'm going to say ddx. I'm going to say x is my variable here. Inside, I'm going to write my function. I'm going to type 74 minus 9e to the negative 0.5x. It will automatically fill in the x here, the same variable that you typed in over there. And where do I want to deal with this? At x equals 15, and you can use the arrows to move over. I'm going to try to do this on here, but it's not going to look great, I don't think. I'm going to do n deriv. I'm going to say d dx. I'm sure you can't see this. 74 minus 9 e to the negative 0.3x. I want to deal with this at x equals 15, and you're going to get the same answer the other calculator gave me. Now, what is this telling me? This is telling me at t equals 15, the water in the tank is, well, since my derivative is positive, that means the volume of water is going to be increasing. So it is increasing at a rate of, well, what I got over here. I'm going to follow the AP rules of accurate to 3 places, so 0.030. And as for the units, I told you in the notes that our units are going to be the units of V divided by the units of T. V is measured in liters, T is measured in seconds, so I'm going to say liters per second. That is the rate of change of the volume. The water is increasing at a rate of 0.030 liters per second. Now, there is another way we could deal with this on the calculator, which may be a little bit easier. I think I've previously shown you how to store variables in the calculator. Sorry, not store variables, store functions in the calculator. If we go back, since we're going to have to use this a couple times, push y equals, and in y equals, we type that function 74 minus 9 e to the negative 0.3x. Then when I go to do my n deriv, I can push variables. I can go over to y variables. I can say function and select the name for y1. And especially if we have to use a function over and over, I think this will be particularly helpful. N deriv y1 comma x comma 15, or if you use this notation, you're just going to select the name for y1 in there. My derivative is 0.030 liters per second. In part B, I want to find the average rate of change of the amount of water over that interval from 10 seconds to 20 seconds. Well, average rate of change means I need to use that formula, f of b minus f of a over b minus a. Here I'm going to do v of 20 minus v of 10 over 20 minus 10. I've shown you before how to evaluate functions on the calculator, especially now that we've stored that in y1. I can just go to the calculator. I can go to the calculator and I can push variables. I can go over to y variables, select the function, select y1, say in parentheses 20 minus y1 of 10. By the way, even though I'm typing it like this on the calculator, they would not accept this notation on the AP exam. Write it in terms of like normal function notation using the functions we have here. Just realize this is how you're going to type it in. I think I'm just going to push enter, and then I'm going to divide that by, in parentheses, 20 minus 10. I'm getting an average rate of change of about 0.043 liters per second. .043 liters per second. By the way, just about everything in this unit we will be using calculators for. So we do need to figure out how to do these derivatives and evaluating things on the calculator. Question number 2 is a little bit different. Please take a moment, read question number 2, and see if you can then store the function in the calculator and get a value of s of 2.4, not s prime, just s of 2.4, and then we'll talk about what it means and get the units. Okay, so I'm going to store that in my calculator under y1. I'm going to say 5 minus the square root of x. Just using x rather than t, it doesn't really matter. And to evaluate s of 2.4, I'm going to go to y variables, y1, and in parentheses, I'm going to say 2.4. I'm getting about 3.451. S of 2.4 is about 3.451. Here's where it gets a little bit strange. Oil's being siphoned out of a tank, being removed from a tank at a rate of that gallons per hour, where T is measured in hours. Okay. I already gave you a rate, as opposed to in problem 1, where I gave you a formula that was a volume. If I give you a rate, well, S of 2.4 is just exactly what this function is 3.451 gallons per hour. This is the rate that oil is being removed from the tank, because the function I already gave you was the rate that oil is being removed. I'm going to interpret this by saying, at t equals 2.4, and by the way, anytime you're asked to interpret, make sure you refer to your specific instant, your specific time when we're dealing with this. So at 2.4, I'm going to say oil is being siphoned out at a rate of 3.451 gallons per hour. This is not how much oil is in the tank. This is the rate that oil is being removed. I would like to see if you can use the calculator to go calculate S prime of 2.4. Send that answer into Edpuzzle, and then we'll figure out the interpretation together. All good? Okay, keep going. I'm just going to keep recording. Okay, we're using n-deriv again. I'm going to find the derivative of the function that I have stored in y1, comma x, comma, my time is 2.4. Hopefully you could get about negative 0.323. Now, the derivative always represents the rate of change. What's strange is originally we were given a rate of change. So this is kind of like the rate of change of the rate of change of this problem. There's a better way to talk about this. I think that I already gave you guys in class in the last unit that example of back in last April when we were dealing with COVID. The governor of New York kept talking about how the number of cases is increasing, but increasing at a decreasing rate, and that was something good. That's kind of what we have going on here. The amount of oil is still, leaving at a rate like that, but the rate that it's leaving, all good? See you later. The rate that it's leaving, that rate itself is decreasing. Let me try to write this out. I'm going to say at t equals 2.4. The rate that oil is being siphoned out, is being removed, that rate itself is decreasing because the derivative of that rate is something negative. It is decreasing at a rate of, I'm just going to say 0.323. I'm not going to include the negative because the negative is taken care of by saying that word decreasing. And now I need to figure out the units. The units of a derivative are the units of the original divided by the units of your independent variable. So the units are going to be gallons per hour, because that was the unit of S, divided by the units of T, gallons per hour per hour. The better way to say this, and you've seen this if you're taking physics, we're just going to say gallons per hour squared. This is not the rate that oil is leaving, see you later, not the rate that oil is leaving the tank. This is the rate of change of the rate that oil is leaving the tank. I know the rate that oil is leaving, but that rate itself is decreasing. These are tricky. And number 1 and 2 are very different because of what the function I gave you actually stands for. Make sure this is all in your notes, and then we're going to go back to your notebooks. Okay, back in your regular notes. If I go and integrate f prime of x dx, which is like saying we're going to integrate a rate of change. If we integrate a rate of change, well, by our first fundamental theorem of calculus, this should give us f with b plugged in minus f with a plugged in. I'm going to say f of b minus f of a. What is this? Well, f is like the amount of the original thing. This is the amount at time b minus the amount at time a. We're going to call this our net change. The integral from a to b of f prime of x dx equals f of b minus f of a. If you integrate a derivative, if you integrate a rate of change, you get the net change in something. Let me write this down. Given a function g of x that already represents a rate of change. If we have some function g of x that represents a rate of change, kind of like number 2 on that worksheet where I gave you the rate that oil was leaving the tank, the net change over the interval from a to b is the integral from a to b of g of x dx. If I give you a function that represents a rate of change and you integrate that function from a to b, you get the net change. Now, as for the units, going to be the opposite of what we did for our derivative. The units are the units of f of x times the units of x. And I feel like this will also make more sense once I show you an example. Make sure that's in the notes. I'll pause the video and then we'll go back to the packet. In your packet, let's take a look at number 3. 30 grams of a pollutant in a lake at time t equals 0. If the number of gallons of pollutant changes at this rate, determine the amount of pollutant in the lake after 12 days. Well, if I was to integrate that function from, from 0 to 12, I would get the net change in the pollutants in the lake. Well, we can do this on the calculator just like you can do derivatives on the calculator. I would like you on your calculator to go store that function in y1. Push y1 and say 1 minus 3 e to the negative 0.3 root x. Now, the integral function is right below the derivative function. Push the math button. Scroll down to option 9, fn int. If you have a calculator that brings up fn int, well, it's going to take 4 arguments. The function, comma the independent variable, comma the lower limit, comma the upper limit. I'm going to type in here y1, comma x, comma 0, comma 12. If you have a newer calculator, it's going to give you something that looks like this. Well, really, you're just going to type things in the way we wrote it over here. I'm going to put 0 as my lower limit, 12 for the upper limit. I'm going to insert the name for y1 over here, unless you actually just feel like typing that whole thing in. And I'm going to say d, I guess I'm going to say x if I have x's stored in y1. Push enter. It's going to take a while to do this. Derivatives are pretty quick calculations, but integrals, it's really doing like a right endpoint sum or a left endpoint sum or a midpoint sum with like 1,000 regions, 10,000 regions. It's going to take a while for the calculator to do those calculations. Here, I'm getting negative 6.578. My units are the units of this times the units of that. Gallons per day times day, that's just gallons. Which means the amount of gallons in the tank, the change in that is negative 6.578 gallons. Now that wasn't exactly my question. I wanted to know how much pollutant is still left in the lake. I was starting with 30 gallons. You're going to say 30. You're going to add this net change to it, this net change that is removing some of the pollutants. I guess we could just jump straight to 30 plus negative 6.578. Do that on the calculator, and you're going to get, whoops, I did that wrong. You're going to do, let's see, 23.422 gallons. The integral gives us the net change, but then I need to add that to the initial amount that you had. There were 30 gallons of pollutants. I added the net change to it, got the final amount of pollutants. Read 4, store the function in the calculator, but then we need to talk about how to set up the integral. All good? Thank you. Okay, so for this one, I'm going to, you know what, I'm not even going to, oh, no, I might as well store it in the calculator. Okay, we're going to say 3 times the natural log of x squared, and that's all in there. Whoops. 3 times the natural log of x squared. Now, your starting temperature is 220 degrees. There's something a little bit different with the language here. I'm not telling you how the temperature is changing. I'm telling you how the temperature is cooling. I've already added in kind of the sign to what's happening over here. Therefore, I'm going to subtract the total amount that the pi has cooled in this time. To find the total amount that the pi has cooled, I'm going to integrate from, well, let's see, I'm starting at 10 minutes, and I'm going to 15 minutes. I'm going to integrate from 10 to 15 that function, and since they didn't give the function a name, I might as well just write the whole function out over here. You can give it a name, don't call it like y sub 1 of x, that's calculator notation, they wouldn't accept that. Create something like, I don't know, capital T of t equals, and then everything, I don't know. Go to the calculator and see if you can do this, and send the answer into Edpuzzle. Okay, 220 minus fn int. I'm going to integrate that function, which I've stored in y1, from 10 to 15. I think I'm getting a final temperature of 144.431 degrees. The reason I automatically subtracted, though, rather than added that thing was because in 3 we were just told how the pollutant was changing. In 4, I told you explicitly the pi is cooling at that rate. So the sign was already basically factored in. Thank you. We're going to head back to the regular notes. There's one more thing we need to get in there. Something else we talked about earlier in the year, but we've got a little bit more to do with this. Given a function, h of x, its average value. See you Friday.
Yeah.
Its average value is 1 over b minus a times the integral from a to b of h of x dx. The average value of a function is defined by the integral of that function from a to b with a 1 over b minus a out front. The units are, actually they're just going to be the units of h. Why? Well, you integrate. You integrate, you're going to get units of h times the units of x. But because of this thing, you're going to divide by the units of x. So you're just going to get, well, the units of h of x. The x is kind of like cancel out names. Get this in the notes, and then we're going to take a look at the packet. Back in your packet. Number 5, take a moment and store that function in your calculator. Please get that in y1. Oh, you know what? Now would probably be a great time to make sure your calculator's in radian mode. Everything in here has got to be done in radians. I think we're there. Part A, I want to know the average temperature in that time period. Part B, I want to know the average rate of change of the temperature. Well, to figure out the average temperature, I'm going to use that formula that I just gave you, 1 over b minus a times the integral from a to b of your function. T is the hours after 9 a.m., so 9 a.m. would be 0 hours after 9 a.m., and 9 p.m. would be 12 hours after 9 a.m. So I'm going to do 1 over 12 minus 0 times the integral from 0 to 12 of t dt. Make sure you are distinguishing, though, between the capital there and the lowercase there. What you're going to do on the calculator is you're going to do your fn int, you're going to get an answer, and then divide it by 12. See if you can give me the number that you get for your answer. Let's see, I'm going to go do my fn int. I'm going to integrate that function from 0 to 12. Enter. And then I'm going to divide this by 12. 58.913, I believe. I told you that the units would be just the units of our function t of t, which means my units are just going to be degrees Fahrenheit, which I feel like should make a little bit of sense. What's the average temperature that day? About 58.913 degrees Fahrenheit. Part B wants to know the average rate of change of the temperature over that time period. Well, if I have a function and want to know the average rate of change of that function, here's where we use our f of b minus f of a over b minus a formula. I'm going to find t of 12 minus t of 0 over 12 minus 0. Go to the calculator and figure this out. I think it's going to be kind of an interesting number answer. Okay, that was stupid. I didn't have to divide that by 12. I'm just getting 0. Average rate of change of the temperature, well, it's kind of like you were warming up in the morning and then cooling down in the evening, and those rates of change kind of cancel each other out. My units are going to be degrees Fahrenheit, units of T, divided by the units of little t, so degrees Fahrenheit per hour. Two different averages here. Average value here, average rate of change here. However, it gets a little more involved than this. Take a moment, read number 6, store the function in the calculator, and then stop. Okay, this is the water this is the rate that water is leaking from the tank. How much water has leaked out of the tank by time 10? Well, I need to do an integral to do that. If I integrate my rate, I get my net change, which will be, well, the total amount of water that has left the tank. I'm going to go and I'm going to integrate my rate from 0 to 10. Integrate the rate, we'll get the total amount that has come out of the tank. Go to the calculator and do that, please, and make sure when you send your answer in, you're including units. $23.655 gallons. Remember that our units, when we integrate, are the units of the function times the units of our independent variable, gallons per minute times minute, just gallons. Now, this is different than what's happening in Part B. In Part B, I want to know how much water is in the tank at time 10. Well, I started with 100 gallons. I know how much has leaked out. I think if I do that 100 gallons, minus, and I'm subtracting here because, again, the sign was kind of included in the fact that I told you it was leaking out, it was getting removed at that rate. If I do 100 minus the integral from 0 to 10 of r of t dt, or I could just say 100 minus that 23.655 gallons that I already got, I think we're going to get there are 76.345 gallons left in the tank. There's a difference between A, where I just found the net change, versus B, where I then applied the net change to how much was in the tank initially. Read C and D. C is what is the average rate that the water is leaking out of the tank. D, what is the average rate of change of the rate that water is leaking out of the tank. Now, you should notice there's a little difference in the language. In Part C, I want to know the average rate that water is leaking out of the tank. You might think that that's the f of b minus f of a formula over b minus a, but it's not. If I want to know the average of the thing that I give you, we use 1 over b minus a times the integral from a to b and all that stuff. I gave you a formula that was the rate that water was leaking out. I want to know the average of the rate that water was leaking out, the average of that thing that I'm giving you. Therefore, part C is going to be 1 over 10 minus 0 times the integral from 0 to 10 of r of t dt. Part D, the average rate of change of the rate that water is leaking out of the tank. I know the rate that water is leaking out of the tank. I want to know the average rate of change of that thing. Because I want to know that, here's where I'm going to do r of 10 minus r of 0 over 10 minus 0. All these questions keep going back to is how was the function originally defined? Did I give you a volume or did I give you a rate initially? I would like you to go to your calculator, do part C and send in your answer, including the units. Seems like about 2.366. We said that for averages, the units are just the units of r of t because the integral and the division kind of cancel each other out in terms of units. So I'm going to say gallons per minute because that's how r of t was measured. Please go do the calculation for D, send in the answer, and see if you can figure out the units there. .232 gallons per minute, so gallons per minute squared will be the units for the average rate of change of the rate that water is leaking out of the tank. We're going to do just a little bit more of this. Before we do that though, make sure all this is in your notes. Turn the page. I'd like to see if you can read the problem, store the function in your calculator, and try to do part A, please. Send in the answer for part A. I know the rate that cars are going through the intersection. If I want to know how many total cars have gone through the intersection, I can just integrate that rate over my time. I'm going to say the integral from 0 to 30 of f of t dt. By the way, I guess I never explicitly said this, but you have to write out these integrals and any derivatives that you're trying to find. I can't just see a number answer. You've got to see the problem. I've got to see the problem that leads to that answer. If you're doing a derivative, don't just give me the answer. Say f. Well, actually, we'll do that in a moment. Let's see. I want to integrate that thing from 0 to 30. I am getting, is this right? Yep, I think so. I'm getting 2,474.078. All of the problems said to round to the nearest whole number because we're talking about cars here. So I'm going to say 2,474 cars passed through the intersection in that 30-minute time period. Now, is traffic flow increasing or decreasing? Again, I kind of keep going back to the COVID stuff. Is the number of cases, so the number of cases is still going up, but is it going up at an increasing rate or a decreasing rate? Is the rate that I gave you, is that f of t increasing or decreasing? Well, to do that, we have to look at the derivative. Specifically, we're going to look at the derivative at 7. You need to show work for this, and by work, I mean you need to write out f prime of 7. Now go to the calculator, use the n-deriv feature, and tell me what f prime of 7 is. Negative 1.873. I think that's all I need to tell me that traffic flow is decreasing because the derivative of the traffic flow f prime of 7 is negative. And I should say that t equals 7 because f prime of 7 is negative. Make sure you're referring to the 7 in your justification. I'd like you to read C and D. and I'd like you to tell me through Edpuzzle, will C involve f of b minus f of a over b minus a, or 1 over b minus a times the integral from a to b of my function? Which one do I have to do in C versus what I'm going to do in D, and use the two to compare? What am I doing in C? Average value of the traffic flow, average of the thing that I gave you. I gave you traffic flow, I want the average of the thing I gave you. That's going to be 1 over b minus a times the integral from a to b of f of t dt. As opposed to D, where I want the average rate of change of the traffic flow, the average rate of change of the thing that I gave you. That means f of 15 minus f of 10 over 15 minus 10. Go do letter C and send in the answer with units. Sorry, 81.899. The units are the units of F, so cars per minute, and decimals are perfectly fine here because this was a rate rather than a total amount of cars, so that'll be okay. Go do D and send that answer in. At 1.518, units are the units of F, cars per minute, divided by these units, cars per minute, so cars per minute squared. There is one last problem I need to show you, and then we'll finish up the packet tomorrow. Take a moment and read number 8, please. I have two different functions here. I have E of t and I have L of t. Well, let's see. I'm starting with 200 people at the fair. Some people they're entering at this rate, they're leaving at that rate. I want to figure out how many people are at the fair 3 hours after it opened. Well, I'm going to start with 200 people. Let's see. There are 200 people at the end of the first hour. I want to know how many people are there at the end of the third hour. Well, I'm going to integrate the rate that people are entering the park from 1, the end of the first hour, to 3, the end of the third hour. 200 people plus however many people have entered. However, that's not good enough, because at the same time, people are also leaving. How many total people have left? Well, I can integrate the leaving rate also from 1 to 3. This is what my problem is going to look like over here. You know what? We can simplify this a little bit. Because both of these integrals have the same limits of integration, I can combine them into a single integral and say 200 plus the integral from 1 to 3 of E of t minus L of t dt. To do this on the calculator, I'm going to store E of t and L of t in different functions. Under y1, I'm going to store E of t, 30t squared, plus 16t in y1, and I'm going to store 12t, really x, minus 3 in y2. And then when I go to type this in, I can say 200 plus fn int of y1 minus y2, comma x, comma, I'm going from 1 to 3. Please tell me how many people rounded to the nearest whole number. By the way, this is at the end of the first hour. That's why we're starting our integrals at 1 rather than 3. That's where we have the 200. Tell me how many people rounded to the nearest whole number are in the park after 3 hours. Let's see. Oh, wow. I wasn't expecting an exact number there, but whatever. We're going to go with it. I'm predicting about 482 people in the park. Tomorrow we're going to spend a lot of time working with, well, how can I work with two functions in general and try to make sense out of both the number of people in the park increasing or decreasing. We'll save all that stuff for tomorrow. And that's all that I have for right now.